Alright guys, this is a real quick video on the natural log and the number e. So as we've been talking about logs, you may have seen or wondered what this thing called the ln button is on your calculator. So you might have seen this button on your calculator right by logs that's just an L and an N, or I guess it's like this on your calculator. And it stands for something called the natural log. So we're going to spend a lot of time in class talking about this, but this is just like a very quick introduction that you need to watch before class. So when we think of the number pi or the number I, we now know that both of those things are actual numbers. It's just we say them differently and we call them pi and I because they have like an extremely intense value. For example, pi is irrational. It's 3.14, we know that, but it goes on forever, and none of us can memorize the entire number because the digits go forever. That is the same thing with our new number today, e, the number e. So the number e is approximately 2.72, but I put a bunch of dots afterwards because it goes on forever. It's actually 2.718, and then it continues from there. But a lot of the times when you work with e, you will just estimate that it's around 2.72. The reason that e exists is because it's helpful for us when we use logs if e is the specific base. So normally we're used to log base 10 of something. So we're used to log base 10. And then we also know that if it's not 10 and it's something else, we know how to get rid of it and change it to back to log base 10. And log base 10 is the common log. So here's where e comes into play. When we have log base 10, we know we use log. But if we have log base e of any number, like in this example here, if we have log base e of something, instead of writing it as log base e, we write it as the natural log of whatever that number is. The natural log, just like the common log, it's always a base 10. The natural log is always a base of e. So if we use that information here, if I see ln of 2 right here, if I see ln of 2, then that's really just saying the natural log base e of 2. So the natural log always has a base of e. There is no way to make it something different because that is simply why the natural log exists. So we should always assume base e. That also means if we look at this example here, I'm going to name it 1. Example 1 says the ln of e. Well, the ln of e is still saying that it's a base of e, which means that it's ln base e of e. Now, we can still use all of the rules. That's the great thing about ln, natural log. We use the same exact rules that we use for log with natural log. So I can use the change of base formula here if I wanted to, and put ln of e divided by ln of e, which simplifies to 1. So the natural log base e of e is just 1. Example 2. Example 2 says the ln of 24x minus the ln of 12 equals. Well, I'm just asking you for these 5 examples to simplify. So I just want to point out using this video, these all can use the same rules. So if I see subtraction here, and I know that these are both natural logs, I can combine them using the quotient rule, just like I could a regular log. So the quotient rule says that I can combine these two to be 1 and switch it from subtraction to division. So it's 24x over 12. Well, I can simplify that because 24 over 12 is just 2. So instead of 24 over 12, I'm just going to write the ln of 2x. Next one says ln of 3 plus ln of 4d. Natural log of 3 plus the natural log of 4d. Well, something plus something means I could just use another one of the log rules, this time the product rule, and it says that if it's addition separate, I can combine them together and multiply them. So I take 3 and I multiply it by 4D, that's 12D. And for now I'm done. I'm just showing you the rules that you can use just like logs. It shouldn't be much different. The ln of s to the 5th power. Well, remember that the ln of s to the 5th has a base of e. Now, with the power rule, it's the only one we haven't used yet today, the power rule says that I could take this exponent using logarithms and bring it down and in front and make it multiply. So I could switch this to be 5 times ln of s. Make sure they look a little different. This is an s. And it's base e. Now I could get a number. If this was like ln of 6, I could get a number, but it says the ln of s. I'm just going to make this clear for everybody. 5 times the natural log of s is done. There's a variable here. I don't know what the natural log of s is because I don't know s. Moving on, the natural log of e to the 7th power. The natural log base e of e to the 7th. Well, I'm looking at this, I'm just trying to simplify. I first know that I can use the power rule and bring this down and in front, this 7, so I could say this is equal to 7 times the natural log of e base e. And I know that the natural log of e base e from example 1 just turns into 1. So now this is just 7 times 1, which gets me 7. And finally, this is number 6. Solve for t to the nearest 10th. So another reason that e exists is because in exponential models in real life, e, a continuous growth rate, is used a lot. You're going to see this on the benchmark. You're going to see this on the regions. So I just wanted to reference this. This is one of many word problems that we will be doing. This isn't even really a word problem, but it describes a situation. So I'm going to write this down here so that I have more space. And that should be a 20,000 like this. I don't know why the comma's at the end. So solve for t to the nearest 10th. Okay, well, I know still, just like logs, the natural log always gives me an answer for the exponent. So if I see what I want to solve for is t, and t is in the exponent, my brain immediately goes off and says, I need to use natural log. The reason I'm going to say natural log this time instead of log is because this e here exists. If this was just another number, then I would just put log on both sides. But because we're using e, this is where you have to make sure you remember the difference. Do I put in a log or do I put in a natural log? Well, most of the time, we're like 100% of the time, if you see e ever, you should use natural log and not regular log. So just like I do normally, I'm going to want to solve for this exponent, which means I'm going to want to use the power rule. So I'm going to take the natural log of both sides. And that's great for me because now, oh, you know what? I messed up. I don't want to take the natural log of both sides first. The reason I don't want to do that is because I could have made this simpler before I got there. It's not that I'm wrong. I could continue the way I just did, but I actually see that 50 is just being multiplied by e. And instead of creating 50 in this and using it, I'm just going to actually divide 50 away first. So on both sides, I'm going to divide by 50. Because 50 over 50 here gives me 1. And I'm just left with e to the 0.03t power. And 20,000 over 50, you don't need a calculator. You can cross out a 0 here and a 0 here. This is now 2,000 divided by 50. Well, I know that 20 divided by 5 is 4, and I add 2 zeros. So this is 400. And now I'm going to be able to solve using my natural log on both sides because, again, I still now have t in the exponent, which means I need to solve for an exponent, which means I need to use logs. Now I know I could use log or natural log, but because this is e, I want to make sure I use natural log. So I'm going to put the natural log on both sides. I'm going to say now I can use the power rule here and bring this down in front. So now I have 0.03 t times the ln of e, or the natural log of e, equals the natural log of 400. Okay, well, I know that the natural log of e base e is just 1. So that can go away entirely because times 1 doesn't matter. So now I have 0.03 t equals the natural log of 400. And I want to solve for t, so I divide by 0.03 on both sides. T equals. Now, in your calculator, you make sure you use the natural log button instead of the log button. You go to your calculator, you take the natural log of 400, which gets you approximately 5.9915, we'll say, and then divide that by 0.03, and you should get about 199.715, but I believe it told us to round to the nearest tenth. So that means only 1 decimal point. So just 199.7 as my answer. This is just a really quick review. You might notice there's not a lot of questions. This is just for you to make sure that you have some reference before we start talking about this in depth in school.